Today we will study the inductance of single-phase two-wire transmission line. First of all, let me tell you what is meant by inductance. It's the property of a conductor or a transmission line to oppose the alternating current flowing through it. Just like the resistance can oppose the current flowing through it, with the help of this property called inductance, the transmission line can oppose alternating current flowing through it. When DC is flowing through the conductor, this property inductance has no effect on it. This inductance comes into the picture only when alternating current is flowing through the conductor. The knowledge of the parameters like inductance, resistance and capacitance will help us in the design of transmission and distribution lines. This inductance is equal to the flux linkage divided by the current flowing through the conductor, and its unit is Henry. Now consider this current carrying conductor. Suppose a current of I ampere is flowing through this conductor, and throughout the length of the conductor magnetic flux lines will be produced. These are the flux lines produced by the current carrying conductor. Now we look at the cross section of the conductor. This bluish circle represents the cross section. Actually, the flux lines will be produced both inside and outside the conductor. These are the magnetic flux lines produced within the conductor, and these are the flux lines produced outside the current carrying conductor. So we have both internal flux and external flux in the conductor. Inductance can be calculated as flux linkage divided by current. So you need to find out both internal flux linkage and external flux linkage. So the total inductance will be equals L internal plus L external, where L internal is the inductance due to the internal flux and L external is the inductance due to external flux linkage. Now we'll see the steps to find out the inductance of a transmission line. The first one is Ampere's circuital law. Ampere's circuital law is integral H dl is equal to I. The magnetic field intensity H along any closed path equals the current enclosed by the path. This closed integral represents the closed path. And from this Ampere's circuital law, we find out H, magnetic field intensity. The second step is to find B, magnetic flux density, which is equal to mu, the magnetic permeability, into H. The third step is to find the flux, which is equal to flux density into area. The fourth step is the calculation of flux linkage, which is equal to the number of conductors into flux. The last step is the calculation of inductance, which is equal to flux linkage divided by the current. So these are the 5 steps usually we use to calculate the inductance of a transmission line. Now let us find out the inductance due to internal flux linkage. Now we consider a conductor of length 1 meter. Throughout the calculation of inductance of transmission line, we consider the conductor of length 1 meter. We are going to find out the internal flux linkage. So now we consider a small strip of thickness dx at a distance of x meter from the center, and this conductor has a radius of r meters. Now this is the strip we are considering. We will find out the flux linkage of this strip. Then we can integrate it from 0 to r, so we will get the total internal flux linkage. First of all, we will apply the Ampere's circuital law. This is to find the magnetic field intensity. The Ampere's circuital law says the magnetic field intensity along any closed path is equal to current enclosed by the path. Now we consider this bluish path which has a thickness dx at a distance of x meter from the origin. So you can represent this magnetic field intensity as hx and the current enclosed by the path as ix. So you can write this as hx into integral dl is equal to the current enclosed by the path as ix. So it is hx into, what is the length of the closed path? Is the bluish circle. The length is 2 pi x, the perimeter of the circle we are considering, is equal to, on the right hand side you have to write the current enclosed by the path. This is not the total current because we are considering only a portion of the conductor. This is the current enclosed by the path. What is the current flowing through this area which is marked with the red lines? This is not equal to I, it is less than the total current I amperes. How we can find out the current flowing through this small area? We have to use the formula current density into the area we consider. The current density can be calculated as the total current divided by the total area. Here the total area is pi r square into the area that we consider, that is pi x square. Actually this is the current flowing through that reddish area. Now hx is equal to this pi and pi getting cancelled. So this x and this x will be getting cancelled. So this is equal to ix divided by 2 pi r square. Now we have to find out, the next step is the calculation of the flux density. So B is equal to, flux density is equal to mu into H, where mu is the relative permeability. Sorry, it's the permeability. So this is equal to mu Ix divided by 2 pi r square. This is our flux density. Now we have to find out the flux lines. The flux phi is equal to B into the area we consider. Here this dA represents the small area through which the flux lines cross. Actually, the flux lines move in this direction. The flux lines move in this direction. The flux lines within the conductor move like this. So these flux lines cross a small strip which is hatched here, which is having a thickness dx, because we considered a small strip of thickness dx. And what is the length? Length is 1 meter, because we consider the conductor of 1 meter length. So what is the area through which the flux lines cross, which is equal to the area equals 1 meter length into the width is dx. This is the area through which the flux lines pass. So phi is equal to B into 1 into dx. So I can write phi is equal to B into dx. So here B is equal to mu I x dx divided by 2 pi r square. Now we have to find out the flux linkage. That's the next step. Flux linkage is equal to number of conductors into the flux lines. Now what is the value of N? Actually we do not consider even a single conductor. Now we have considered only a portion of the conductor, because this is the conductor we considered. This is the conductor, and we consider only a small portion of the conductor, which is having a radial length x meter. So we cannot put n is equal to 1, as we have considered only a portion of a single conductor, and that fraction is equal to pi x square divided by pi r square. This area is a small fraction of the total area pi r square. So that can be written as pi x square divided by the total area pi r square into flux. So which is equal to this pi and a pi getting cancelled. So it is equal to x square divided by r square into, what is phi? Phi is equal to mu I x dx divided by 2 pi r square. So this is equal to mu I x cube dx divided by 2 pi r raised to 4. So this is the flux linkage within the small strip of thickness dx that we considered. Now we have to find out the total flux linkage within the conductor. How can we calculate the total flux linkage? Psi is equal to the total flux linkage is equal to integral 0 to r mu I x cube dx divided by 2 pi r raised to 4, which is equal to mu I divided by 2 pi r raised to 4, these are all the constants, into integral 0 to r x cube dx. So this flux can be written as psi internal because this is the total internal flux. So this is equal to mu I divided by 2 pi r raised to 4 into, what is the integral of x cube? It is x raised to 4 divided by 4. The limits are from 0 to r. So this is equal to mu I divided by 2 pi r raised to 4 into r raised to 4 by 4. So the total internal flux is equal to this r raised to 4 will be getting cancelled. So this is equal to mu I divided by 8 pi. This is the total internal flux. Next we have to find out the L internal. L internal is equal to the flux linkage divided by current, which is equal to this mu I divided by 8 pi divided by I. So this current I and I will be getting cancelled. So this is equal to mu by 8 pi. So L internal is equal to mu divided by 8 pi. And mu can be written as mu 0 into mu r divided by 8 pi. You can assume that mu r, the relative permeability, is equal to 1. And what is mu 0? Mu 0 is equal to 4 pi into 10 raised to minus 7. So which is equal to 4 pi into 10 raised to minus 7 divided by 8 pi. So which is equal to this pi and the pi getting cancelled. So this can be written as 10 raised to minus 7 divided by 2. This is our internal inductance, or the inductance due to internal flux linkage, and its unit is Henry per meter. Usually the unit of inductance is Henry, but here we considered the conductor of 1 meter length. So inductance is 10 raised to minus 7 by 2 Henry per meter. Now we will find out the inductance due to external flux linkage. First of all, we need to find out the total external flux. For that, we consider a small strip of thickness dx, which is at a distance of x meter from the conductor. Now this strip is considered external to the conductor, and this is within 2 points P1 and P2. Both are external points. P1 is at a distance d1 meter and P2 is at a distance of d2 meter from the conductor. And the strip we consider lies between the 2 points P1 and P2. First of all, we will find out the flux linkage within the strip. Then we can find out the total external flux linkage using integration. Let's first apply the Ampere's circuital law. Integral H dl is equal to I. The magnetic field intensity along any closed path is equal to the current enclosed by the path. Now it is H into, what is the total length of the strip we consider? You see, this is the strip we consider. The total length is the length of the perimeter, length of this circle, which is equal to the perimeter of this circle. Which is equal to H into 2 pi x. This is equal to, what is the current enclosed by this path? Now we can take the total current. It is equal to I amperes, because the complete current is flowing within this path we consider. So H is equal to I divided by 2 pi x. The next step is the calculation of flux density. B is equal to mu into H, which is equal to mu into I divided by 2 pi x. The next step is the calculation of flux lines. Phi is equal to B into the area we consider. Here also dA is equal to the area of the strip, which is the length into breadth. It is equal to 1 into the breadth is dx, because we considered a strip of thickness dx. So flux is equal to mu I divided by 2 pi x into the small area we considered is dx. The next step is the calculation of flux linkage, which is equal to n into phi. Here n is equal to 1, because we are considering the whole conductor. Because when you consider the closed path, which is shown by the orange line, the complete conductor is within this path. So n is equal to 1. So 1 into mu I dx divided by 2 pi x. This is the flux linkage within the strip we considered. What is the total external flux? We need to integrate it. And when we integrate it, we need to consider the 2 points P1 and P2. We have to integrate it from the point P1 to P2. So we'll get the total flux linkage. Integral d1 to d2. These are the two external points we considered, d1 and d2. So we will get the total external flux linkage within this area. Mu I divided by 2 pi x into dx, which is equal to mu I by 2 pi is a constant into integral d1 to d2 1 by x dx. Which is equal to mu I divided by 2 pi into natural logarithm of x from d1 to d2, and this is equal to mu I divided by 2 pi natural logarithm d2 minus natural logarithm of d1, the upper limit minus the lower limit. So this is in the form of log a minus log b. So you can write this as mu I divided by 2 pi into log a minus log b is equal to log a by b. So natural logarithm d2 by d1. This is the total external flux linkage. This is a general expression to find the external flux linkage from the 2 points, between the 2 points d1 and d2. Now see, these are the 2 points d1 and this is the point P1, this is the point P2. The first point is at a length of d1 and second point is at a distance of d2 from the conductor. Now actually the external flux lines link from the surface of the conductor from this point to any point, say D, which is external to the conductor. So this D1 can be replaced by the length R, which is the radius. Because these flux lines exist from the surface of the conductor. So this is equal to mu I divided by 2 pi into natural logarithm d by r, because here the r is the radius of the conductor, because the external flux starts from r, from the point r. External flux starts from the surface of the conductor. This is the total external flux. Instead of D2, we can write it as D, because there are no D1, D2 hereafter. We have only one external point. So this can be written as D instead of D2. So this is the total external flux. external flux linkage. So what is L external, which is equal to psi divided by, again it is psi divided by the current, the flux linkage per current. Which is equal to mu by 2 pi into, the current will be getting cancelled, ln natural logarithm d by r. And this mu is equal to, as you know, it is mu 0 into mu r divided by 2 pi into natural logarithm d by r. Again, mu r is equal to, the relative permeability is equal to 1, and mu 0 is equal to 4 pi into 10 raised to minus 7. So this can be written as 4 pi into 10 raised to minus 7 divided by 2 pi into natural logarithm d by r. So this is our external flux linkage, sorry, external inductance. This pi and pi will be getting cancelled. So this is equal to 2 into 10 raised to minus 7 natural logarithm d by r. This is the inductance due to external flux linkage. What is the total inductance? Which is equal to L internal plus L external. What is the internal flux linkage? This is our internal flux linkage, 10 raised to minus 7 by 2 Henry per meter. Here also the unit is Henry per meter. Internal flux is 10 raised to minus 7 by 2. This 10 raised to minus 7 by 2 plus 2 into 10 raised to minus 7 natural logarithm d by r. If we factor out 2 into 10 raised to minus 7, this is 1 by 4 plus natural logarithm d by r. So this can be written as 2 into 10 raised to minus 7. 1 by 4 can be written as natural logarithm e raised to 1 by 4. Actually, this natural logarithm and e will be getting cancelled. So 1 by 4 can be written as natural logarithm e raised to 1 by 4 plus natural logarithm d by r. So this is equal to 2 into 10 raised to minus 7. It is in the form of log a plus log b, which is equal to log a into b. That is natural logarithm e raised to 1 by 4 into d divided by r, which is equal to 2 into 10 raised to minus 7 natural logarithm. The c raised to 1 by 4 can be brought to the denominator. So it becomes c raised to minus 1 by 4 into r, which is equal to 2 into 10 raised to minus 7 natural logarithm d divided by e raised to minus 1 by 4 can be calculated using a calculator. This is equal to 0.7788 into r. It can be written as 2 into 10 raised to minus 7 natural logarithm d divided by r dash. This r dash is equal to 0.7788 r. And this product r dash is called geometrical mean radius of the conductor. It is geometrical mean radius of the conductor. So this is our total inductance of the conductor, 2 into 10 raised to minus 7 ln d by r dash. Now we will find out the inductance of single phase two-wire transmission line. What is the inductance of one conductor? It is equal to 2 into 10 raised to minus 7 natural logarithm d by r dash. This 2 into 10 raised to minus 7 natural logarithm d divided by r dash, which is equal to LB, the inductance of the second conductor. So the total inductance is equal to, or the inductance of the two-wire transmission line is equal to 4 into 10 raised to minus 7 natural logarithm d by r dash Henry per meter, because we are considering 1 meter length of the conductor. This is the total inductance of a single phase transmission line.